Today we're going to talk about average atomic mass and how to measurement. The first thing we need to talk about when we talk about average atomic mass are isotopes. Now, if you remember, isotopes are naturally occurring variants of an element. Remember that hydrogen had three types of isotopes. It had protium, deuterium, and tritium. Okay, and they vary because of the number of neutrons they have. All three of those are hydrogen because they have one proton, but protium has 0 neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. So those natural elements are all hydrogen. They're just different types of hydrogen. So in order to get our average atomic mass on our periodic table, for example, hydrogen has 1.00795. Well, like I was saying before, if neutrons and protons are roughly the same size, how come it's not a whole number? We don't have half of neutrons and half of protons. So where does that decimal come from? Well, that decimal comes from the percentage of the types of isotopes. Okay, so the average atomic mass is an average of the abundance of the naturally occurring isotopes. So that abundance being the percentage. Okay? So it's a weighted average. Okay? So this is something that we can actually calculate. Okay? We find out, or we know through experimentation, how much of a percentage there might be of protium, or how much of a percentage there is of deuterium, etc. And then we can take those percentages and then we can average them together. Okay, the unit we use to measure this is the AMU. It's called the atomic mass unit. Okay, and it is equal to 1/12 of the mass of an atom of specifically the isotope carbon-12. And that's one of the really ingenious things about the periodic table, is that all of the atomic masses are based off of carbon-12. Later on in the year, we will talk about something called a mole. And the mole is the quintessential unit of the periodic table. And it all derives from carbon-12. Okay, we'll talk more about that later. So carbon-12 being that there are 12 particles, 6 neutrons, 6 protons, and 1/12, since protons and neutrons are about the same weight, is about the weight of an AMU, is about the weight of a proton or a neutron. Okay, so the mass of an atom in AMUs is roughly equal to the sum of the number of protons and neutrons in a nucleus. okay? We use the AMUs of an isotope of its abundance to calculate mass. All right, so what I can do is I can explain to you a couple of examples, and you can also use those examples to predict certain types of isotopes on Earth, and I'll show you what I mean here in just a minute. So let's go over an example here. The element copper naturally occurring isotopes with mass numbers of 63 and 65. The relative abundance of the isotopes are 69.2% and 30.8% respectively. Calculate the average mass. So what we're going to do is we're going to use those percentages in decimal form, okay? We have a isotope mass number of 63, and we're going to multiply that by our 69.2%, okay? And I'm going to change that into a decimal form for percentages, and I'm going to multiply that by 0.692, okay? I am also going to take my 65 and multiply it by my 30.8. So I've got 65 times 0.308. All you need to do is just move that decimal over 2 places. And I'm going to add those two calculations together. So I end up with 43.596, and I'm going to add that to 20.02. And what I end up with is 63.616 as my average. All right, so copper 63.546, that was pretty close. Now, one of the things that you can do is when you get a average like this, if you are given an example and you can say, what is the most likely highest abundance isotope? Well, 63.616. Now, this one's a little more difficult because of the rounding, but 63 isotope has a 69.2%. So 63 is much higher percentage than a 65, okay? And 63.616 is much closer to 63 than it is to 65. We'll do that with another example here. Let's make up an element. A research team just discovered a new element, and it was called fortium. And they discovered the following isotopes. Fortium 138 has an abundance of 44.7%. Fortium 139 has 52.3%. Fortium 140 has a 0.5%, and fortium-141 has 2.5%. And we're just going to do those same calculations. We're going to move the decimal over 2 spots. Okay, and this right here is where I see the most mistakes happen, is people don't add a 0 in for those really small numbers. But 138 times 0.447, we're going to add that to 139 times 0.523. I'm going to add that to 140 times 0.005. I'm going to add that to 141, try and squeeze this in here, times 0.025. Sorry, it's so small. All right, and we're going to do those calculations, add all of those together, and we end up with 138.608. Okay, now again, let's round that number. We're going to round that to 139. An isotope of 139, a mass number of 139. Well, look back at our original numbers here. Who has the highest percentage? 139. So we can use that average atomic mass to usually guesstimate which isotope has the highest abundance. Okay, if we go back and look at our 3 hydrogens, protium, deuterium, and tritium, this has 1 proton, this has 1 proton and 1 neutron, and this has 1 proton and 2 neutrons. And we can roughly guesstimate the AMUs by saying this is equal to 1 AMU, this is equal to 2 AMUs, and this is equal to 3 AMUs. Well, if you look at hydrogen, hydrogen has an average atomic mass of 1.0078, excuse me, 1.00795. Now, what is that closest to? 1, 2, or 3? Well, it's closest to 1 AMU, which actually means that most of the hydrogen throughout the known universe is protium. Deuterium and tritium are out there, but they are in extremely small amounts. Okay, so protium is the most abundant hydrogen in the universe. All right, we'll do one final example for the day. If nitrogen has an average atomic mass of 14.0067 grams, which isotope of nitrogen has the highest relative abundance? Nitrogen 14 or nitrogen 15? Well, what you're going to do is you're going to take that atomic mass and you're going to round it. When you're going to round that down to 14 grams or 14 AMUs. That means that nitrogen 14 is the highest relative abundance. It has the highest percentage of isotopes of all the nitrogens. Okay, so it's that plain and simple. You just need to be able to calculate your average atomic masses, add them together, and you need to be able to pick out your relative abundance based off of the rounded average atomic mass. Okay, and again, I want to stress that atomic mass and mass number are 2 separate things, but you can use atomic mass to guesstimate mass number, and in this case we're guesstimating our isotopes. Okay, that covers atomic mass. Next class we're going to talk about radiation and half-life. All right, remember, work together, help each other, and make the world a better place. See ya.